Okay, good afternoon. The class average is pretty good, about 71 based on the total weighted average, including the first 2 midterms and the 5 assignments. Okay, and so if you maintain that level of performance, you should have no problem in passing this course. And if you maintain the same level as you are now, you can expect to get the same or better grade. So if you are in the green, for example, if you maintain the same in the final, you should be expecting an A. Okay, and if you are in the second quartile, then it's probably a B, and in the third quartile, it'll be a C. Okay, that's what you are aiming at. So I hope that you will maintain that performance, and I don't have to give any D. I don't take any pleasure in giving Ds, but you need to take the course seriously. You cannot just blow the final exam and still expect to pass. Okay, that's the only requirement at this stage, because all the others who would have failed have left the course. So you guys are sticking out, and I think you're doing well. And I hope you have learned a lot from this course. I have tried to challenge you at a fairly high level in terms of MATLAB as well as in terms of mathematical modeling. I am teaching 2176 next term, so hopefully most of you will come there, and we will continue building the mathematical model. So the last 3 lectures, I'm not really introducing any new features of MATLAB, but reinforcing what we have learned to solve chemical engineering problems in particular. So the current assignment you have is reinforcing some of the things that Tom covered for plotting, subplots, and producing plots with several curves on the same graph. Okay, so if you have any questions, I guess the only time we have is today after the class, between my next class, 1:30 and 3 o'clock or so. I'm traveling tomorrow, so I won't be in here, and then you have a big break. I should be back Tuesday morning in the office if you have any questions, okay, on the current assignment. The last 3 lectures, yeah, question?
Are these lectures being uploaded as videos like previous ones?
If I get the time, I will do that, yes. I am recording it, but since I'm traveling, I may not be able to do it right away, but when I come back, I will upload that, yeah. Any other questions?
Will we receive a sort of study guide for the final or anything like that?
Nope. Study guide? What do you mean by study guide? No, I'm gradually trying to wean you out of that process, right? The first exam, I basically gave you an assignment that was very similar. The second one, the third one in terms of the final exam in terms of format will be exactly the same as the second midterm. A mixture of MATLAB commands and problems with errors. And as you see today, the programming gets a bit more complicated as we are learning to handle a bit more complicated problems in chemical process design. Okay, so the structure will be the same, but there won't be any study guide. I have already given you a hint. That is, the problems that we see in the last 3 lectures, some of them will appear in the final exam. So make sure that you understand the problems. And
well, the conversion from binary to being on the
everything that we have seen in this course. The final exam is on the whole course, right from day 1. Okay. So it will be a mixture of problems from all those different stages. Yeah? Don't hesitate, come on. No questions? All right, okay. So what I'm going to do today is build on a problem that we have already seen and you have solved, and that is the multi-component distillation problem. But we are going to escalate the level of difficulty a little bit, and I will explain to you what the situation is, and then we will see how to write the MATLAB code. And I have put the code already in the notes. It's on Moodle. You can download it. I won't be able to cover, there are about 110 lines or so in the code. I won't be able to cover the whole thing. But I'm going to introduce features that are variations that we are building slowly on things that we have already learned. Okay. Ultimately, my desire, and I guess we will fulfill this desire in 2176, is to build this up all the way to Aspen. So we'll take an Aspen simulator and do a flash calculations and show all the equations that have gone into Aspen. So we are building through that process. Now, in the last lecture, I looked at this problem of an absorption column, how to design, how to analyze the performance of an absorption column. These are nothing but mass balances around each stage, okay, so and 2171 type of material. And you don't have to develop these equations in this course. I have given you those equations, but you should be able to understand and formulate it for solution by MATLAB. And then the equilibrium relationships are given in this form, y equals kxi. K is the equilibrium ratio. Typically it comes from a thermodynamic model. It may be a constant under certain circumstances and not a constant, function of temperature and pressure under other circumstances. And the same set of equations can be solved in a couple of different ways. One is arranging as a matrix, and that results in a tridiagonal matrix. And the other one is eliminating all the intermediate variables and relating only the input and the output concentrations. That is basically what chemical process design is about. You have a process unit, and you know what you're putting in. You want to predict what the output is going to be. So a relationship between the input and output using conservation laws, using mass conservation, energy conservation, and using thermodynamics, etc. So there are three different variations of that model that I have given you here. Be familiar with these and additional ones that I may throw up in the final exam. Okay? But basically you need to understand, when I give you an equation like this, it has lots of symbols. I explained to you the meaning of each one of these symbols. L is the liquid rate, V is the vapor rate, K is the equilibrium ratio. So S is defined, Y1, Yn plus 1, all these are defined. And when you have so many different symbols in that, if I give you one as an unknown and everything else as a known, you should be able to solve it. Okay? And MATLAB fsolve does that, whether it is linear or nonlinear, it doesn't matter. It will solve the equation as long as you pose it in the correct form. Identify what is the unknown term so that fsolve can solve for that unknown variable. And you need to write a function describing that equation. So it may be one of the three equations that is most appropriate for a given problem in the final exam. Okay? And as I said, there will be an exam question on this particular absorption problem. I'm not saying what type of problem, but it will be one of the variations on the problems that using these equations. So study them carefully. Okay, now the other one that we have seen is the multi-component flash, what we considered as isothermal flash, and I'm going to now show you a generalization of that. The equation again remains the same. This is the equation that we have seen. We know how to code it in MATLAB. Okay, but what is the problem? The basic problem is you have a separation device, simply a tank, into which you feed a certain mixture, in this case propane, butane, and N-pentane, a three-component system. Okay, and at a given temperature and pressure. And if you control the temperature and pressure in such a way that it splits into two parts, a vapor with a composition Yi and a liquid with a composition Xi. Okay, and our task as a process engineer is to find out what fraction goes as vapor. So we define psi as P divided by F. Okay, F is the feed rate. So you're putting the feed at a certain rate, and you want to know what fraction goes as the vapor. Now the first class of problem that we have seen in this one is one where the temperature is a constant and the pressure is a constant. You know that. Once you know the temperature and pressure, you know the K values, the equilibrium ratios. Those are constants. That's the kind of problem that we have seen. So if K is constant and you treat psi, the vapor fraction, as the unknown, and you try to solve for that, what fraction is vapor? And once you find the vapor fraction, then you put the vapor fraction here, you can calculate the liquid composition, and once you know the liquid composition, you can calculate the vapor composition. So you know what vapor fraction is, and what is the composition of the vapor, and what is the composition in the liquid. Unfortunately, what happens in real life is the temperature is something that you don't know beforehand. Maybe you want to control it. Okay? Meaning I want to adjust the temperature in such a way that 50% of the feed goes as vapor. In such a specification, what I'm telling you is I know psi, but I don't know what the temperature is. I know the vapor fraction is 0.5, but I don't know what the temperature is. It's the same set of equations, but the problem specification has changed. Okay? So in such a case, if the temperature is unknown, I get into immediate difficulty, because if I don't know the temperature, I don't know what the K values are. I cannot give you the K values a priori. Okay? But there is a relationship between the temperature and the K values for each component. So this equation, can you see it at the back? Okay? So this equation will allow you to calculate K1, K2, K3 in this particular case, okay, because there are three components. So these three components, once you know the temperature, you put the temperature in here and you can calculate what the K values are. Then use the K values in here and see whether the function is satisfied. Okay? Please, if you don't understand the problem, ask me questions, because I expect you to be able to deal with variations on this. In the exam, I might give you a situation where this relationship is replaced by K as a function of both temperature and pressure. And then I might ask you to find the pressure. Okay? So the temperature and pressures are the control parameters that you have as a process operator. And by adjusting this, you can adjust what fraction will go as vapor, and hence what is the composition, what is the separation. So in this particular case, you have propane, N-butane, N-pentane. Propane is the most volatile material. It has the lowest boiling point. So if I start with these three mixtures in a tank as a liquid and I start adding heat, gradually increasing the temperature, I will reach a point when propane will begin to vaporize because it has the lowest boiling point. And as I continue to increase the temperature, then butane will start to evaporate, and then pentane will start to evaporate. If I keep on adding heat, increasing the temperature above the boiling point of pentane, all of them will go to vapor. So try to understand the process. Okay, I'm starting with a liquid, I'm adding heat. First propane starts boiling, and then butane, and then pentane. Now the first temperature at which the propane begins to boil is called the bubble point temperature. Okay, and that's a very important parameter. So we want to be able to calculate what a bubble point temperature is. Okay, the similar concept exists for bubble point pressure as well. Okay, so the temperature at which propane begins to boil, that means what would be the vapor fraction at that time? Yeah, very small number, approaching zero, because I have the first bubble, so the vapor fraction is very small. So if I put psi equal to 0 in this and then ask what is the temperature, I will be able to get an answer out of that. That will be my bubble point. Okay? And then, as I said, I continue to increase and all of it goes to vapor. Now imagine a situation where the whole thing is in vapor state because the temperature is so high, and then I start cooling. Okay? When the temperature hits the boiling point of pentane, pentane will begin to condense from the vapor phase. That will be called the dew point. Okay? So the column has to be operated between the bubble point and the dew point of that vessel. These are two important parameters. So at dew point, what do you think will be the vapor fraction? Approaching 1, right? Because all of it is vapor, only one drop forms as a dew. Okay? So the vapor fraction is 1. So by putting vapor fraction into 1 in here, I'll be able to calculate the dew point. So the same formalism, same set of equations will allow me to calculate the bubble point temperature and the dew point temperature. Similar idea exists for pressures also, bubble point pressure and dew point pressure. Okay? You should be able to solve for these from an equation like that. So in the final exam, I might give you an equation and say, I want to solve for bubble point pressure. Is this program going to do it? You should be able to answer that, yes or no. And the program has some errors. Can you fix it? Okay? So those are the kinds of things that I would expect you to be able to do. The same thing with the absorption column, and in the next class we will see a fluid mechanics problem with a net pipeline network. Okay? So these three problems, variations of these will be in the final exam, and you should be able to handle any one of them. So far, any questions? So, do you understand the problem? The problem is, given a vapor fraction, find the temperature. Okay? So psi or T can be considered as an unknown. In the first problem, you are given determine the vapor fraction psi and the composition. Okay? And you are given the temperature as 750 degrees and the pressure as 400 psia. Okay? So what is the vapor fraction? That's a standard problem that we already know. Okay? And the second problem is, what should be the temperature in order to get 50% of the feed into the vapor? Now psi is given as 0.5, and you are asking what should be the temperature so that I achieve 50% in vapor fraction. Under those conditions, what is the composition in the liquid, composition in the vapor? The third question is determine the dew point temperature. That means psi equal to 1. And the fourth part is determine the bubble point temperature, psi is equal to 0. We may not have time to do all of them, but we will see as much as we can, and then the program is in the notes. You should be able to study for the rest. Okay, so we have basically one single equation that we need to program. We have already done this kind of a program before. The only variation, improvement, is we need to construct this program in such a way it has t and psi as variables. But one of them will be identified as an unknown, the other one as known. Either one can be an unknown. Okay? So we need to generalize that particular equation to handle that kind of a case. And then we will use it with fsolve as we have done before. Okay? The second part that we need to worry about is that this k is no longer a constant number. We used to give 5 numbers or 6 numbers, depending on it's a 5 component or 6 component. But k is no longer a constant. It is given by a function. So I need to write a separate function that will accept a value of t and then calculate and return the value of k. So you see something about the modular nature of how we structure these programs. So I'm going to write first a function that will accept t and a and calculate k and return those k values for every component. Okay? I must make it in such a way that I can use it with propane, butane, pentane, or with hexane, heptane, octane, whatever the number of components. The component is identified by these numbers. And these numbers are given in the book by Holland. There is an entire book devoted to multi-component distillation, and there is an appendix there that lists these constants for various types of hydrocarbons. Okay? And again, notice that book was published in 1963. That was the status then. Now we can actually calculate these k values using thermodynamic models, using fugacity concepts, which we will see in the next course as we go move on, and as you do the thermodynamic course. Okay? And Aspen will include all of the latest technologies, latest equations, latest models to solve the same problem, to answer the same type of questions. Okay? So you're going to see progressively more complicated, more rigorous model that will allow you to design such columns. Okay, let me start. So as I said, I need to write a function for calculating the k value, and then a function for calculating this. And I need to generalize it in such a way that it can accept either t or psi. And then, of course, I need to program these to be able to print out the compositions in both liquid and vapor phase. And I need to structure all these in such a way that I can get a solution for a given set of numbers. So we are going to do that in MATLAB. And again, what would you like me to do? I have written the program. I have put it in the notes. Shall we take that function and then go through it to understand, or you want me to write it? Which one is more beneficial to you? Write it with all the mistakes that I can make. Because you have the notes, correct me if I make any mistake. Okay? Because I think you need to get to that level of comfort where you understand the problem, you're going to start writing. Don't be afraid of making mistakes. You can figure out those mistakes and fix them as you go along. Okay? So as I said, I'm going to write a function. I have a function called k value, but let me just make it old so that I don't reuse it. So my first task is to write a function that will calculate the k values given the coefficients a and the temperature. Okay? So I say k val.m. I'm going to write a function which will accept as input a and t and return k as the output. Okay? So function, what will I have as an output? K, because I'm calculating k, right? Equals k val, and I'm going to have a comma t as the input. What is a and what is t? Okay, let me see whether I can. I need to switch between these two to show you both. Okay, so a is all these matrices that you see, the numbers here. Okay, so a will contain 4 values for each component. So it's a vector of 4 values in a row, and I'm going to have as many rows as there are components. So I'm going to define a matrix A, and I don't want to type all these, so I'll just cut that part and paste it into this. Okay, and then my real goal is to take those values of A and the value of T and calculate that particular expression and return K. So if you have the notes, keep this equation open in front of you, okay? And I'm going to be able to program that, and I want you to help me with doing it right. Okay, so you can put any comments here. This function returns k values, okay? And what would be my statement like? This is going to be done for each component. So what I expect is A is a row vector of coefficients. Okay, and T is a scalar number. Just one number, temperature. At that temperature, I want to calculate the k value of that particular component that corresponds to the row. Okay, so how can I do that? If I make A as a row vector, then I can take A and multiply it by, I guess I need to go back and forth. You may have it in front of you. So when you expand this, maybe I should expand this for j equals 1 to 4. Okay, so it will be something like ai1 t to the power 0 plus ai2 t to the power 1 plus ai3 t squared plus ai4 t cubed. That's what I will get when I expand the summation. I is the component number. I once means propane, I equals 2 means butane, etc. Okay, so that is, these are all I. Okay, so I have 4 numbers in A, and I need to multiply it by t to the power 0, t to the power 1, t to the power 2, t to the power 3, and then add them up. And then I need to raise this whole to the power 3. Why? Because I have 1/3 in here. Okay, so raise both sides to the power 3 and then multiply it by t. That is the formula I want to input into that particular function. Any questions on this? Do you understand what I'm trying to do? Okay, so let's go to that function, and so A times 1 t square t cube k equals t cube multiplied to the power 3 star t. And do you think that's right? What have I done there? A, I'm treating it as a vector. So when A comes into this function, it's going to have 4 numbers, which is a row vector. Okay, so it will have 4 numbers corresponding to ethane or propane or butane or whatever. Okay, and I'm multiplying that by a vector, and that vector is 1 t squared t cube. When I put that multiplication, what is going to happen? That is a vector multiplication in MATLAB terminology, right? Any ideas? Will that work? That's what I'm asking you to do. This is the kind of thing you need to do in a... Pardon me? One at a time? Yeah, one suggestion is I need to put the dot. That's perfect. I can. You want me to put the dot there, right? If I put the dot, it will take A1 multiplied with 1, A2 multiplied with t, A3 multiplied with t squared, etc. And then I can pass it to the sum function to sum that. Any other suggestions? Now, these are the variations. I might give you this without the sum, then you have to identify it as an error. Or I might give you this, then you have to identify what the error is. Now, if I put this, what am I trying to do? I'm creating a row vector containing 1 t squared t cube. I'm transposing it into a column vector, and A is a row vector. So what will that product produce? It will produce a vector product between 2 vectors. And what is that vector product? It automatically sums it. It is A1 times 1 plus A2 times t plus A3 times t squared plus A4 times t to the cube. So this function should work as it is. Okay, so there are many ways of implementing that, and these variations are the ones that I'm going to kind of check. Okay, I'll put one of these variations and see whether you understand whether it's an error or not an error. And if it is an error, fix the error. Okay? Any questions on the variations that I've talked about? How many of you don't understand what I've talked about? So that means we're doing well. You understand the vector product, yeah.
So you just also define A in the workspace now?
I need to define A when I call this, from wherever I call it. Maybe the workspace, it may be another function. Okay, wherever I'm calling, I have to make sure that A is a row vector and T is a scalar. And using that T as a scalar, I'm constructing a vector here, which is a row vector, and then I'm transposing it into a column vector. And then I'm doing a multiplication between A and T. That vector multiplication sums it also automatically, because that's how a vector matrix multiplication is defined. Yeah?
Why don't we need a period behind, like,
You can put a period. You can make this work. What you want to achieve is take every, A is a vector, right? Take every element from A, multiply by the corresponding element in the vector 1t, t squared, t cubed, and then add them up. So this is one that will do based on the definition of what a matrix product is in MATLAB. Okay? But if you don't make this as a column vector, and if you do this, then it will do an element by element multiplication, and it will return a vector of the same length as either A or T. Both of them should have the same number of elements. But it will return the product as a vector. Okay? And so I need to put a sum. They both will produce the same result. That's what I'm trying to tell you. Okay? If you don't understand that clearly, you need to go into MATLAB and play around with it. For example, A is equal to 1, 2, 3, 4. It's a row vector. And X is equal to 1, 2, 3, 4. This is a column vector, right? Now, if I say A times T, A times X, what is it going to do? Oops, cannot see that. That is, produces a single number. What is that number? That number is essentially product of A1 with X1 plus A2 with X2 plus A3 with X3. Okay? Now, that produces 30. Now let's take A dot star X. Now it produced A1 with X1, A2 with X2, A3 with X3, but a vector. Now if I pass this to sum, A dot star X, oops, X transpose, then it produces 30 also. There are two ways of doing the same thing. Does that answer your question? Do you understand? Okay. Anybody else? So that is the k-value function. Okay. So let me save that. And the next thing I need to do is write a function for the flash equation itself. Okay. We have done that many times, so I'm just going to copy that part. But I'll show you what the difference is, because I'm afraid that we will run out of time. Okay. So this is a function that implements the flash equation. Okay. The flash equation, like k minus 1 times z divided by 1 plus psi k minus 1. You have programmed this, you have looked at it many, many times. Okay. So the only variation I have done is I have included all the a values inside this function that was given to me in the table. So it is a 3 by 4 matrix, but the first row has the material for ethane, second row for propane, third row for butane, etc. And the way that I have written this one is it has only psi as the unknown. I am solving the very first problem where temperature is given and psi has to be found. Okay, so the temperature is given as 750, so I defined that. Z is given as 0.3, 0.3, 0.4, the feed composition. I defined that. And then I find out how many elements are there in Z. And this is the difference. From line 16 to 18, you tell me, what am I trying to do? Make a call to that function called k-value that I wrote just now. Okay? And to that, I'm passing the value of the temperature, and I'm passing the value of A for each row. When I equal to 1, only the first row. Now there is an error between this and what I wrote for k value. What is the error? I guess there is not. Okay, I had it as. Can you see? Oh, am I jumping the gun? Because if I'm not writing it, I guess you need to follow quickly what I'm trying to do. This is a function that implements the flash equation that we have seen before, and what I'm trying to show you is how to include in it the calculation for k values. Previously, the k values were just 3 numbers. I would define k as equal to whatever the number is, 3 numbers. Now I'm getting those 3 k values. N will be 3 because there are 3 elements in here, 3 components. Okay, n will be 3. So I make this call 3 times to k value, and I'm passing what the temperature is, and I'm passing which particular row it has to take to the k value function. And then the k value function will calculate the k, return it, and I store it in k1, k2, k3, etc. 3 times. And once I have the k value, the line 19 is the same as I've done before. I calculate the function. Okay. Now, the way, yeah, question?
Wasn't your k value A then T?
Yes, that's what I wanted to see whether you would notice. Okay. Here I have the order mixed up. I wrote it as A and T, but in the function that I have put the order as T and A. So you have one of 2 choices. Go back and change this to T and A, T comma A. Okay, those are the kinds of errors that I will throw in so that you can see whether you'll be able to catch or not. Okay. So now I have written a function that calculates the Rice-Rashford equation. This is called the Rice-Rashford equation. And by the time I come to line 19, I have defined Z, I have calculated the appropriate values of K at that temperature 750 by adding this piece of code. Instead of a line where I say K equals 231 or whatever, I have added this piece of code which is in modular fashion, meaning it will call another function, get the numbers, build the array K, and then use it to calculate F. Okay? Any questions on that? Now, how do I use this to solve the particular problem? Okay, I need to save this. I need to save the K value. And then I go to MATLAB and I call fsolve. Oops. And I give it the name of the function. The name of the function is fcd psi. Okay, that's the function that calculates the flash equation using Charles D. Holland. That's a guy, his correlation for k values. So I just named it as fcd. Psi is the unknown. Okay, what do I need to provide as a guess? This is fsolve. You should know what I should do. A guess for psi, because I'm solving for psi. Okay, and it has to be between 0 and 1. So let me try 0.5. 0.6270. That's a vapor fraction. Okay, so it's a fairly easy thing to do. Okay, now I'm also asked to calculate the composition, liquid and vapor composition, and I'm given the equation for this. So I may actually want to write a script that calls these and calculates the vapor and liquid fraction. Okay, so let me edit L11 script. Okay, so the first line is going to be psi is equal to fsolve at what was that? fcd psi comma 0.5. Okay, so that is the one that actually makes a call to that particular function I wrote, which makes a call to the k values, get the k values at those temperatures, and using 0.5 as the initial guess returns the psi. The next thing I need to do is calculate the x and y values, the liquid and the vapor compositions under these conditions. So I need to look at those equations, and the equation is x equals z divided by 1 plus psi k minus 1. Okay, so I need the k values here again to calculate that. Okay, so if you have these notes in front of you, give out these equations to me as I type. Okay, otherwise I need to go back and forth. So I want to calculate x values, okay? So x is going to be equal to, can you tell me what the equation is? Z?
divided by, open parentheses,
Z? Say it again.
Z
Divided by?
open parentheses, 1 plus psi, open, k minus 1, close, close.
Does that look right? And y is equal to k times x with a dot. Okay? So these are the basic equations I need to be able to calculate the liquid composition and the vapor composition. Okay? Now Z is going to be the feed composition. So I need to define what Z is. Z was defined inside that function. Okay? So if I open that function, Z is defined here. Okay? So I can just copy this and paste it into the script. Okay, so I have defined Z, which I need in line 5. Psi is calculated from the particular problem that I am solving. How about K? Where do I get the K values? I don't have K values here. Okay, so there are a couple of options for you. Can you think of some options? Copy that code and put it here, right? You can take that code and paste it there. And of course, in order to do that, you also need to define the t value. Okay? But you also need to define one more thing. What is that? The values of a, the coefficient, right, in the script file. Okay? So you can go there and copy these values and paste it there. Okay, what I'm trying to do is I'm trying to write a script that will solve that particular equation, get the vapor fraction, and then using that vapor fraction, calculate the compositions in the liquid and the vapor stream. Those are the equations that are given to me. Okay, oops. The equations in line 12 and line 14, x and y. But in order to calculate x in line 12, I need z, which I know, but I have defined it in the other function, so I need to put it in the script file also. Okay, so I've done that here. Then I need to have the values of k. So I'm copying the coefficients of a, make a call to k val once again, get the values of k, and now I will be able to use those values of k here. Okay. Are there any questions on the script file? Good question. Do I need to index k? Okay, k has index here. K is going to be 3 numbers, k1, k2, k3. That will be calculated in the for loop 9 to 11. But as it comes out, k will be a vector. Now the question is, can I use a vector here? If I use the vector, -1 would mean each one of the k values will be subtracted and then multiplied by psi. Psi is a scalar number. Each one of them will be multiplied by psi, and then 1 will be added to each one. So the entire denominator will be a vector containing 3 numbers. And then I have the dot divide. Okay, that will take care of z divided by k. Okay, but it says that there is an error here. What is the error? Invalid syntax, missing parenthesis. So I have to do I have to put one or take one out? Put one. Okay, then it matches with the first one in the denominator. And I'm not putting a semicolon because I wanted to print x and print y. Okay, so that is the script. With this script, if I run it, I should be able to get the compositions in the workspace if everything works fine. Undefined function n. Do you know where I made the mistake? I have not defined n, so I should have n as equal to length of z. Z is defined before. Okay, so do that and run it one more time. And there you get your x and y, and of course above that you must have your psi also. Okay. Now I'm going to ask you a question. If I do sum of x, what do you think I'll get? 1. Why is it 1? Sum of mole fractions, right? Sum of y is also equal to 1. Those are the ways that you can check whether everything is going right or not. Okay. So that's the first part, the answer to the first question. Okay, and the second question was, now I need to reformulate the problem in such a way that I have the vapor fraction as the unknown. Sorry, the temperature as the unknown. Vapor fraction is given 50%. Psi is known, but I want to solve for the temperature. What temperature will that be true? 50% will go into the vapor. How do I formulate that particular problem? Okay, so I need to write a new function which is the same equation, but this equation is going to have either t or psi, so that I can choose which one is the specification. Okay, so again, let me open up that function in the interest of time, and that is this function. Okay, it's exactly the same function as before, but it has two parameters, input parameters, either temperature or psi. You can pass two of them. And when you pass it to fsolve, fsolve has a clever way to identify which is to be treated as unknown and which has to be given a constant value. Remember, you have only one equation, so only one can be an unknown. The other must be specified. So either you can specify t and solve for psi, or you can specify psi and solve for t. In this case, we're going to specify psi and solve for t. So the generalization I have made is I have allowed for both of them to be input as parameters, and I have to identify which one I am solving when I call fsolve. Until the time I'm going to defer that decision. Okay, and other than that, it's the same. I have the a, I have the z, I calculate the k values, and I have the same equation. Exactly the same. Everything is exactly the same. Only I made the input parameters to contain both t and psi, and when I make a call to fsolve, I will identify which one is going to be the unknown, either t or psi. Okay, so now let's go to the script file and add the second part. Okay, part 2. And what is part 2? It's going to solve for fsolve, but this time it's going to solve for t. T is equal to fsolve at the function is fcdt. But watch the difference. Now this is something that you should be able to kind of learn. We know how to use fsolve. So ask for fsolve and see what are the other features available. One of the features is to identify which variable I'm solving for. So here, after the @ sign, I'm going to put in parenthesis t. That tells fsolve t is going to be the unknown. Okay, and then I leave a space and then put the function name, and the function will take two arguments. Okay, one is going to be t and the other one is going to be psi. Okay, and then I need to provide an initial guess for whichever variable I'm solving. In this particular case, I'm solving for t. So I might put 700. Okay, but I need to fix the value of psi. So I'm going to say psi is equal to 0.5 in a line before. These two lines give you a very powerful way to generalize fsolve using any number of variables where you identify which variable you are solving for, fixing all the others as constants. Okay, make sure that you understand and ask me if there are any questions. This is the solution to the second part. What is the question in the second part? If I want to achieve 50% in vapor, what should be the temperature? So I fix psi as 0.5 and I pass that value. But when I call fsolve, I say solve for temperature. This function will have two inputs, but solve for temperature. Keep temperature as the guessed variable, okay, and iterate on that. Try different values for temperature until that function becomes equal to 0. So this becomes the guess for that particular variable that you are specifying. Okay, so let me show you once more how that function looks. This is a new function. It's essentially I copied it, but I added t and psi as the input parameters. And everything else in that function is the same. I define a, I define z, I calculate the k values. It says this is the beauty of modularizing the function. So k values are calculated in one subroutine. It can be reused for many different problems because it's the same k value function that is given. Okay, and then the function itself is also the same. Okay, it's the same function, but the k values are calculated based on the temperature. But temperature is the one that's going to be guessed now. Okay, so if I run this particular script, if everything worked fine in the workspace, I should get the temperature, 744. So if you control the temperature to be 744 degrees Rankine, then 50% of it will go to the vapor. Am I going fast? Are you guys following? As I said, one question on this guaranteed. Okay? And there are lots of variations, so you really need to understand the programming, because what I'm going to test you on is implementing a particular model. It's the MATLAB part that is going to be tested in the final exam. Okay? So I'll give you different versions of the code and ask you to find what the error is and fix the error if there is an error. Okay? And various types of specifications you should be able to understand. So look at problem 3 and 4, part 3 and 4 in this. The code is given. Make sure that you understand it. If there are questions, please feel free to come and ask me. Okay?